Okay, I think we're recording. Hey, this is an intro video to section 3, which is dealing with how to solve, or that is how to find integrals using the method of partial fraction. Partial fractions is something hopefully we've all seen in the past as far as breaking up a fraction, a rational expression, into the sum of what they call partial fractions, as you can see here. So we're going to take this guy and start working on it. Okay, the way I like to lecture on it is let's take this integral, rewrite it. So it's a busy one, isn't it? X squared plus 2x minus 1, and then downstairs is x cubed minus x. The first thing I notice is that the degree below is bigger than the degree above. If degree of the numerator is greater than or equal to the degree of the denominator, then we have an extra task. We have to perform long division. I know. Haven't had to do that in a while. Okay, that's what you have to do on the problem. So in this case, the degree below is bigger, so we don't have to worry about that. So I'll just recommend, why don't we just start working on this thing and go, all right, so what we should do is, the very first thing is, let's factor the denominator. Let's pull out an x. We're left with x squared minus 1 dx. All right, so now we factor that difference of squares, and we're left with x plus 1, and x minus 1 in the denominator. Agreed? Here's where the partial fraction decomposition comes into play. So I'll rewrite it again. So I'll write it as, therefore, it's the integral, and I look at each of these linear factors, and I can break this guy up into a sum of baby factors, so to speak, that have those denominators. So very quickly, what I mean by that is, I don't know what the numerators are going to be. For linear factors, you just use an unknown constant, okay, looking like this. Maybe this rings a bell with some of you. I hope it does. If not, we're going to go through it. Okay, so we're going to transform our integral, which was, you see what it looks like at the beginning. We're going to make it look like this. And it's all algebra. That's all it is. In fact, I teach this every time I teach pre-calculus. This is what we cover. So what we're going to do is show it to you. What we're going to do is we're going to compare x squared plus 2x minus 1 is this, all factored out. And how the heck do we make it look like what I wrote on this above? Well, hope you're not squeamish about fractions, because what I'm going to do is switch a color here, and I'm going to multiply the entire thing by x minus 1, x plus 1. Now that's bad notation. Don't tell any of your professors I did this, but you're going to bam here and bam and bam and bam. You're going to clear fractions. And when you do so, you get this color, I guess. Well, when you do so, you lose the entire denominator on the left, and you're left with the numerator, x squared 2x minus 1 is equal to a times, what clears is this, x minus 1, and then you have x plus 1, plus b times x minus 1, plus c times x plus 1. And you're left with, well, you got one polynomial equals another polynomial. What you could do, the long way of doing this, is to multiply out the right-hand side and compare x squared coefficients with x coefficients with constants. But with this problem, there's a fast way to do it. And I'm going to switch colors now. I'm going to go back to this guy. I'm going to say, let x equal 0. So this is supposed to be satisfied by all x. In particular, I'm choosing a strategic value of x that causes a factor to disappear. Okay, so if I plug in 0, I get, on the left-hand side, I get -1 because x is 0. Okay, on the other side, on the right-hand side, I get a times x is 0, -1, times x is 0 times 1. And look what happens. This goes to 0, this goes to 0 when x is 0. So what do we have here? We have minus a is equal to minus 1 is equal to minus a, and it tells us that a is equal to 1. We found one of our numerators. Keep going, right? I better switch colors, so I'll switch to purple, I guess. Now, what you do is you inspect your factors. And what I did is I picked on x and I made them 0, but now we're going to pick on x minus 1. So how about we let x equal 1? Okay, if x is equal to 1, on the left-hand side, we have 1 squared plus 2 times 1 minus 1. And on the right-hand side, we've got, okay, 0, 0, and who survives is just c. So we have c times 1 plus 1 is 2. So we're seeing that 2 is equal to 2c. And so we find also that c is equal to 1. Man, we got one more to go. One more to go, okay? So you guessed it, if you know what I'm doing. Now you're going to let x equal negative 1. And it's because of this factor right there. So we let x equal negative 1. Negative 1 squared is still 1, but then 2 times negative 1 is negative 2 minus 1. And on the other side, again, a disappears. This time c disappears, but b survives. This is called the Heaviside cover-up method in one book I used to teach out of. Some guy named Heaviside, okay? And so what we have is b times negative 1, and then negative 1. Am I doing that right? Yeah, negative 1, and negative 1 is negative 2. So we're getting negative 2 is equal to 2b, and look at this, b is equal to negative 1. We found them all. Remember that integral way up here? Way up there. Well, we have it now. We're going to finish this problem off. We're going to say our integral becomes the integral of a, which is 1 over x. Can you handle that one? Minus 1, which is b over x plus 1. And then plus 1, which is c over x minus 1 dx. And upon integration, okay, that's our new integral. All of that was algebra, all of it. This is calculus right here. We integrate, we get the natural log absolute of x minus the natural log absolute of x plus 1. And then plus natural log absolute of x minus 1, and guess what? Plus c. And so our answer is right there. This is what we're doing. It's pretty straightforward section. You got to worry about what if it's nonlinear? What if it's x squared plus 4? Well, then you put a linear factor. You don't just put a constant c on top, but you go bx plus c. A little more elaborate, and you're going to see some of those as well. But this is an introductory problem, and I hope you liked it. I have to stop the recording now. See you at the next one.